Hello and welcome to this presentation. I am Mario Andrés Aguilar-ORDUñA and I'm going to present the paper titled Active Disturbance Rejection Control of a Permanent Magnet Synchronous Generator for Wind Turbine Applications. Let's start by saying that a permanent magnet synchronous generator, or PMSG, is an electrical machine that transforms rotational mechanical energy into electrical energy. Besides a rotor compounded by permanent magnets, a distinctive characteristic of the PMSG is the intimate relationship between the frequency of the electrical current generated and the angular rotor speed. As we are going to talk about wind turbine applications, let's define a wind turbine as a wind energy conversion system specialized in transforming the kinetic energy of the wind into electrical power. Among multiple wind turbine designs and configurations where a PMSG can advantageously be applied, we focus on those wind turbines with a horizontal axis, variable speed, and variable pitch. The amount of power extracted from different wind speeds depends on the configuration and design of a wind turbine. Specifically, for a horizontal axis, variable pitch, and variable speed wind turbine, we have the following four work zones. In Zone 1, the wind speed is too low to overcome the inertia and friction forces to move the wind turbine. So in this zone, it is impossible to extract power from the wind. In contrast, in Zone 4, the wind speed is too high, so the wind turbine must be stopped to avoid damage and failure of the whole system. In this zone, it is also impossible to extract power from the wind. In Zone 3, the wind speed is higher than the nominal wind speed, doing that the permanent magnet synchronous generator works over its nominal speed. So the controller must adjust the blade's pitch angle to limit the power extraction to operate the electric generator at its nominal speed. In Zone 2, the wind speed is higher than the cutting speed, but lower than the nominal wind speed. In this zone, it is possible to maximize the energy extracted by setting the blade's pitch angle at 0 and controlling the rotor angular speed to track the so-called maximum power extraction curve. It's a curve right here. This work zone is where this paper takes place. Now, let's consider a horizontal axis with variable pitch and variable speed wind turbine connected to the grid via a back-to-back converter. Notice that we are considering a direct-driven wind turbine, so the blades are directly attached to the PMSG. This is possible due to the PMSG capability of having a large number of pole pairs. To model the whole system, we consider three subsystems: the blades that convert the wind's kinetic energy into rotational kinetic energy, the PMSG that converted the kinetic rotational energy into electrical power, and the back-to-back converter that manages the power between the electrical grid and the wind turbine. The wind power extracted by the blades is given by this equation, where ρ is the air density, A is the area covered by the rotor's blades with radius RT, Bw is the wind velocity, and Cp is the power coefficient, which was first proposed by Hebertt in 1998. Its parameters have been changing depending on the technology of the wind turbine. This coefficient depends on the tip speed ratio and the blade pitch angle. This coefficient is characterized by the blade's aerodynamic design. We can determine the torque produced by the wind by this equation, and as we consider a direct-driven wind turbine, the mechanical equation is just the equation of a rotating mass. we model the permanent magnet synchronous generator in the synchronous reference frame by applying the Clark transformation followed by the Park transformation to the electrical equations in the ABC reference frame or natural reference frame, determined by Kirchhoff's law. The Park's angle is just the product of the angular position and the pole pair number. Notice the simplicity of the electromagnetic torque expression. It is quite similar to the electromagnetic torque of a DC motor. From the equation of the system, we realize that all phase variables, as well as the control inputs, can be expressed in terms of the angular position, the electric current, and its derivatives. Then, the system qualifies as differentially flat, with the angular position and the current ID as flat outputs. Finally, we obtain the input-output model of the system, deriving the founded flat outputs, obtaining these equations. The grid-side converter connects the permanent magnet synchronous generator and the electrical grid via an RL filter. Similarly, as we model the PMSG, to model the grid-side converter in the synchronous reference frame, we use the Clark and Park transformations, selecting as the Park angle the integral of the electrical grid frequency. Additionally, we also determine the voltage of the DC link capacitor and the instantaneous power exchanged with the grid. Employing the system equations and those of instantaneous power, we observe that the phase variables, as well as the control inputs, are a function of the DC link voltage and the instantaneous reactive power. Then, this system qualifies as differentially flat, with the DC link voltage and the instantaneous reactive power as flat outputs. The input-output model is just given by these equations. For the whole wind turbine, we have 5 control objectives. The first control objective is to track the maximum power extraction curve. Notice that if we vary the rotor angular speed at a certain wind speed, we get a maximum power point. Then, if we do this at different wind speeds, we get the maximum power extraction curve. The second control objective is to reduce the copper losses, commonly manifested as heat in the machine. This is done by regulating the current ID to 0. To inject the active power into the electrical grid, and for the correct operation of the back-to-back converter, it is necessary to maintain the DC link voltage into a suitable value. Then, the third control objective is to regulate the DC link voltage to the desired value. The back-to-back converter gives the capability of controlling the reactive power to the electrical grid. Then, the fourth control objective is to regulate the reactive power into the electrical grid. Finally, the fifth control objective is to synchronize the frequency of the generated currents to that of the electrical grid. To track the maximum power extraction curve, we employ an active disturbance rejection controller. The methodology of this robust control technique dictates that all exogenous disturbances and all endogenous disturbances, like nonlinearities, unmodel dynamics, and parameters uncertainties, are lumped into a total disturbance term. Then, we design an ADRC based on the simplified output tracking error system. Notice that only the flat output, theta, and the control input are measurable. An extended state observer is employed to estimate the unmeasured states and the total disturbance term. The gain parameters are computed to be Hurwitz to ensure the asymptotic stability of the characteristic polynomial of the observer. Then, we propose a control law based on the estimates of the phase variables. Such control law also may include a compensation term of the total disturbance term. One more time, we compute the gain parameters to be Hurwitz to ensure the asymptotic stability of the controller. We regulate the electric current to 0, also track the desired reactive power employing two independent PI controllers designed under the basis of their respective simplified systems. Notice that only the control inputs and the flat outputs are measurable. It is worth mentioning that the gain parameters are not necessarily the same. They are selected independently each other. Similarly, as we did in the previous cases, we use the simplified system to design a controller, which in this case we propose a generalized proportional integral controller, to track the desired reference of the DC-link voltage. We implement the GPI controller via its classical compensation network form. From its characteristic polynomial, we can see that to ensure asymptotic stability of the controller, the gain parameters must be Hurwitz. For the connection between the wind turbine and the electrical grid, we must synchronize the signals of both systems. For that, we employ a synchronous reference frame phase lock loop. The SRF-PLL first employs the Clark and Park transformations to obtain a synchronous reference frame representation of the grid signals, where we can notice that if the Park's angle and the grid angle are equal, then the quadrature component of the grid voltage is equal to 0. Then it follows that if somehow we regulate towards 0 the voltage VGQ, we can obtain an estimate of the grid angle. For that, we use a PI controller. This is the block diagram of a classical synchronous reference frame phase lock loop. Now, to test the performance of the previous controllers, we do some numerical simulations in Simulink MATLAB. We propose a realistic wind profile with an average speed of 11 meters per second, containing wind gusts and turbulence components. The wind turbine, as well as the filter parameters, are taken from the paper of Amen, Payman, and Dacchio, which corresponds to a 5 megawatts wind turbine. For the first graph, we can see that the controller performs well. Notice that the optimal angular velocity tracking error is considerably small, which translates into an accurate tracking of the optimal angular velocity. Also, the ID current tracking error is pretty small, revealing that the ID current is quite close to 0. Zoom at the first 10 seconds reveals the behavior of the system at the very beginning. It is important to say that a smooth trajectory is employed to start the system. By doing this, we avoid excessive forces and stress over the system during the start. These other graphs depict the behavior of the grid-side converter. We can observe that the DC-link voltage is close to its desired value. The reactive power follows the trajectory demanded, representing a supply or a demand of reactive power from the electrical grid. Zoom at the first second, we observe that the DC-link voltage varies 5 volts around its desired value. This effect is due to the changing nature of the wind, which is never constant. This effect is also present in the reactive power graphs. Nevertheless, these variations are quite small. Finally, Notice that the electricity generated by the wind turbine is in phase with the electrical grid. To conclude this presentation, we can say that the differential flatness property exhibited by the PMSG and the grid-side converter is advantageously exploited to design an ADRC controller to track the maximum power extraction curve, a GPI to regulate the DC link voltage to its desired value, also to design two PI controllers to reduce the copper losses and control the reactive power exchanges with the electrical grid. The synchronization between the electrical grid and the wind turbine is made by an SRF PLL, and numerical simulation, which exhibit good performance, supports the proposed controllers. Finally, as further work, we aim to design a sensorless controller, namely avoiding measuring the PMSG angular position to track the maximum power curve, even more, avoiding measuring wind speed. I left here the reference used to develop this work. Thank you very much for your attention, and I hope you have enjoyed the presentation.